Most large language models today don't actually read text, they read tokens. Before a transformer even sees your input, it gets passed to a tokenizer, usually byte pair encoding. What BPE does is simple. It looks at which byte pairs appear frequently, merges them into tokens, and repeats this process until it builds a fixed vocabulary. This works well for compression, but it's terrible for reasoning because tokenization is frequency based, not uncertainty based. So what if compute followed entropy or the uncertainty instead of tokens? That's the idea behind Byte Latent Transformer or BLT. Instead of fixed tokens, BLT works directly on bytes and dynamically groups them into patches. A patch is a variable length span of bytes. If the next byte is easy to predict or the entropy is low, the patch grows. If the model is uncertain or the entropy is high, the patch ends and a new one starts. So predictable text gets compressed aggressively and difficult regions get more attention. This already gives you something tokenizers can't, adaptive compute allocation. But here's the key detail. Patches are not learned end to end by the model. BLT uses a small separate byte level language model to estimate next byte entropy. That entropy gets where patch boundaries go. This happens during data loading, not inside the transformer. But why does this matter? Because it guarantees incremental patching. The model never needs to look into the future to decide how to segment the past. That's something BPE fundamentally cannot do. Architecturally, BLT has three transformers, not one. First, a local byte encoder. It's a small, cheap, and it works with a sliding window attention. Its job is to turn raw bytes into representations. In other words, the information contained in these bytes must be distilled into the learnable patches. Second, we have a large latent transformer. This operates only on patches. This is where most of the compute goes, and because patches are long, this transformer runs far fewer steps than a normal large language model. Third, we have a local byte decoder. Local byte decoder here, it takes the patch level predictions and reconstruct the next byte. Essentially, it is mirroring the encoder, but the difference is that now the patches have a lot of information contained in them, and those information must be distilled back into bytes. So information flows from bytes to patches and patches to bytes using cross attention. So reasoning happens in the patch space, exact generation happens in the byte space. So there's one more important point. Bytes alone are weak. So BLT injects hash-based n-gram embeddings at the byte level. This gives the model subvert and morphological structure without using a explicit vocabulary.